girls, today I'm going to instruct you on how to FOIL two binomials involving radicals and how to rationalize a fraction that it has radicals. First, I'm going to do a quick review of how to distribute a monomial by binomial. This was you had in your last week's work, but I want to make sure that we're good to go with this concept. So if I want to distribute the square root of 7 to both of these terms, I needed to multiply the square root of 7 times the square root of 7, keeping in mind that any time I take a radical times itself, it's what I call my magic trick, that becomes a plain old 7. So square root of 7 times square root of 7 is square root of 49, which is plain old 7, and then square root of 7 times minus 3 stays outside, square root of 7 stays inside. So when I distribute, that is what my answer looks like. These are not like terms. I cannot combine that 7 and that minus 3 because of that radical 7. Similarly here, this is considered one term, this right here. Is 2 radical 2x. So it needs to be distributed times this first term in this binomial, two terms being added together, and then the 2 times radical 2x times 3 radical 2x. So when I'm multiplying, I multiply the outsides. That understood 1. 2 times 1 is 2. And then underneath my radical, when I'm multiplying these two terms together, I get 2x times x, which is 2x squared. Then I'm going to distribute this 2 radical 2x to that second term. 2 times 3 is 6. And then underneath the radical, I'm going to have a 2 times 2 is 4x. And then I'm going to look at those two terms and say, are they like? Not right now. Can I simplify them and see if they're like? So I'm going to get the highlighter out. I'm going to highlight anything that I can simplify. The x squared is perfect. It can come out. And the 4 is perfect. It can come out. So the square root of x squared is a plain old x, which makes it 2x. Then I have this radical 2. Plus the square root of 4 is a 2, which 2 times 6 is 12, and I'll have 12 radical x. And we'll look at those radicals. Are those like radicals? Nope. So that is my simplified answer. Now that we've reviewed how to do a monomial times a binomial, let's look at FOILing. Remember FOILing, what it stood for? First, outer, inner, last. And I'm just going to show you these terms, and I'll highlight in a different color than we're starting to multiply. Remember, you're going to do your first two terms, then your outer, then your inner, then your last. So we're going to do all that multiplication and then see if we have any like terms to combine. So just like we did when there were variables involved, I'm going to multiply square root of 7 times square root of 2, and I'm going to get square root of 14. Then I'm going to multiply my outer, square root of 7 times minus square root of 5, and I'm going to get minus square root of 35. Then I'm going to do my inners. Square root of 3 times square root of 2 is going to be plus square root of 6. And then again, I'm keeping these signs, then plus square root of 3 times minus square root of 5 is going to be minus square root of 15. And now look at all these. Is there a perfect square that goes into 14? No. What about 35? That's 7 times 5? No. 6 is 2 times 3? No. 15 is 3 times 5? So I can't simplify these at all, and none of these are like terms. So as messy as this is, that's as simplified as possible. Okay, let's go over here to example B. Let me pull back out my red. So when I multiply, I'm going to FOIL two binomials, square root of 3x times square root of 3x. Ooh, magic. That just becomes a plain old 3x. Then I'm going to do my outers. The 2 is outside of the radical. The square root of 3x is inside. Cannot interact when I multiply. Then I'm going to do my inners. Whoops. And I'm going to get minus 5 radical 3x. And then I'm going to do my last. A minus 5 times a plus 2 is a, minus 10. I was about to not make it negative. All right. Looking at these, are there like terms? 3x is not like with anybody. Ooh, these two are like terms. So let's highlight them. This is like with this. And I'm just going to add the coefficients. So 3x has nobody to combine with. 2 minus 5 makes negative 3 of those radical 3x's. And then I have that minus 10. And that is my simplified answer when I FOIL those two. Okay, let's think back on we were multiplying in chapter 5. And remember we had something like this. And I said, do not you dare say that this is x squared plus 4. And we talked about it. I made this big drama-rama. I'm going to cry if you do that. Because remember, this is x plus 2 times x plus 2. And you have to first outer, inner, last. So you end up with 3 terms after you've combined. It's the same thing here. You cannot just distribute that and say, oh, this is 6 plus y. As nice as it would be, I have to FOIL it. So I have to multiply all my terms. Everybody gets to dance with everybody else by multiplication. So here's square root of 6 plus square root of y times square root of 6 plus square root of y. I've got to write it out twice, then I have to FOIL. So square root of 6 times square root of 6, magic, becomes a plain old 6. Then I do my outers. Square root of 6 times square root of y is plus the square root of 6y. Then I do my inners. Square root of y plus square root of 6 is plus square root of 6y. And then I do my last, again magic. Square root of y times square root of y is plain old y. Now I look at the situation. Can I simplify the radicals? Can I combine like terms? I cannot simplify the 6y, but I can combine these two together. But be careful. It's not, it's tempting to want to make it 12y, but it's not. We have one of these terms plus one of those terms. So what's going to happen is, when I'm going to show my work up here since I'm out of space, I'm going to say 6 doesn't combine with anybody, then one of those plus one of those makes two of those terms. Just like if it was x plus x. So you have two radical 6y's plus y. And again, these aren't very, very neat, but this is exactly what happens and is as simplified as you can get when you FOIL. This example actually is going to feel a lot nicer because it will simplify, because you have this plus radical 2 minus radical 2. And this is actually what we were doing back in chapter 5. We called it the difference of two squares. That's what this really is going to be. But the radicals, it's not going to look like that. So when I have the square root of 7 times the square root of 7, again, I'm FOILing these two binomials, I'm going to get magic plain old 7. Then I'm going to do the outers, and, oh goodness. Let's see. Okay, then I'm going to do the outers right here, and I'm going to get minus radical 14. Okay, forgive the little issue with the typing, but I'm going to FOIL these two binomials. When I multiply the square root of 7 times the square root of 7, I'm going to get plain old 7. Then I'm going to multiply square root of 7 times negative square root of 2, and I'm going to get minus the square root of 14. Then I'm going to do my inners, and I'm going to get square root of 2 times square root of 7 and get plus radical 14. And then I'm going to do my last, which is going to give me minus radical 2 times radical 2, magic, it goes away, get minus 2. Then here's why this is going to look so much nicer. Because I had minus radical 14 plus radical 14, those go bye-bye. Goodbye, goodbye. And then I'm just going to have 7 minus 2, which is going to equal 5. Now, this just magically showed up here of this heart, which is what I just pointed out. You cannot distribute that exponent across addition. You can distribute it across multiplication or division, but not addition. So this is to make sure. It says caution, and this is what I just pointed out. Anytime I have it, this is what I pointed out a minute ago, x plus 2 quantity squared equals x plus 2 times x plus 2. Great Algebra 1 basic to just know. And then you would have to first, outer, inner, last. Okay, one of the things you have to understand with simplifying radicals is it's just not allowed to leave a radical in the denominator. It's just not okay. So if there's a radicand in the denominator, we've got to get rid of it. And this is what we're going to call rationalizing a denominator. So I'm going to highlight this. And this is the radical 1 over 2x is not simplified because a radical appears in the denominator of the fraction. Not allowed. There is a way to change it, and that's what we call rationalizing the denominator. I'm going to use two powerful things. I'm going to use one, the magic trick, which is that we know the square root of x times the square root of x equals plain old x. And I'm also going to use the power of 1. These are what I'm going to call these to teach you how to rationalize. The power of 1 is x times 1 equals x. Anything times 1 equals itself. So these two little tricks are going to help us get rid of that radical in that denominator. So here's the deal. If I know that the square root of 2 times the square root of 2 equals a plain old 2, we know that if I multiply that denominator by square root of 2, it would make that radical go away. But I can't just do that just because I want to. I have to obey all the laws to keep this fraction the same. But I do know if this power of 1 deal, a little exclamation point by it, if I multiply my top of my fraction, the numerator by square root of 2, and the bottom by square root of 2, that's just a 1. Any number of itself is just a 1. So this right here is the POW, because I'm just going to multiply this by a 1. And what's going to happen is when I do that, I'm going to get 1 times square root of 2 is square root of 2, and then square root of 2 times square root of 2 is plain old 2. And so what I've done now is written this radical expression simplified by rationalizing it. Okay, let's look at a couple more examples. So what if I have this example? What if I have the square root of 5/3? We learned at the beginning of this unit that that's the same thing as square root of 5 over square root of 3. But we're also now realizing that square root of 3 is not allowed. Can't be downstairs. So I'm going to use my rationalizing deal, and I'm going to multiply the top and the bottom by square root of 3. So the square root of 5 times the square root of 3 equals square root of 15. And then square root of 3 times square root of 3 equals plain old 3. And then I've done what I call rationalizing the denominator. And I've gotten rid of the square root, so that now I have that square root of 5/3 simplified to square root of 15 over square root of 3. Press pause and look at it for a minute if you're not sure. Let me show you another example. This example is 4 over, these come out of your textbook, square root of 24x. Now here's the scoop. I don't want to multiply by the square root of 24x on the top and the bottom. I want to see if 24 simplifies. So this is 4 times 6, and the square root of 4 is 2. So I'm just simplifying this radical downstairs and get 2 radical 6x. And hopefully you are becoming proficient enough at your simplifications. Now, I can simplify this 4 over 2 because they're both outside. As long as the fractions are inside or outside, you can reduce them. So that 4 over 2 reduces to this, becomes a 2 over radical 6x. So now I've simplified my radicals. Now I'm ready to rationalize. To get rid of the square root of 6x, I'm going to multiply the top and the bottom by what I want to go away, to make the radical go away. And so then I'm going to have 2 radical 6x over magic trick plain old 6x. And so then the 2 and the 6 are both outside the radical, so I can simplify that. 2 goes into that 1, 2 goes into that 3, so then my final answer is going to become square root of 6x over 3x. I'm going to leave you with a definition of rationalizing a square root denominator from your textbook. And I'll just read it out loud to you. To rationalize a square root denominator, multiply the numerator and denominator of the given fraction by the square root that appears in its denominator, or by a square root that makes a perfect square radicand in the denominator. Again, in your textbook, great examples, actually great videos there. So use that. I'll be available during your Zoom session to answer questions and to reiterate these concepts, but hopefully this was helpful. I wish you well.